All right. So, hello and welcome back to another uh, lecture in the ongoing series of lectures in color reproduction in pre-press repro technique. So, in the last lecture, we had talked about the various inferences that can be drawn from the tone reproduction curves of that is obtained by plotting the density data from the various stages of reproduction. We had also talked about how we can use a special type of graphing tool to take advantage of the fact that the human eye is more susceptible to smaller changes in tones in the highlight area than it is in the shadow areas. So that also we had discussed about. Now, having said and done all this, so let me just go back a little bit earlier. So, for example, we had established that what should be the ideal nature of the tone response curve or tone reproduction curve, whatever you like to call, and how much leeway we have in order to ensure that maximum tones are achieved accurately in our reproduction. So we know for a fact that in the diagram that you are seeing in front of you, that this is the minimum achievable density in the reproduction with respect to the original, and this is the maximum one. And uh, a line which is 45 degrees joining these 2 points is your ideal reproduction curve. However, this is not actually possible, right? Uh, your maximum achievable density in the original is more than 2.5, right, as you can see over at this point, but you are limited to a value of 2 in your reproduction. So what you can do is you can compress the data or you can compress the tones in certain areas of your reproduction so that the curve that you get uh, basically ensures that the overall density or the contrast increases. So how is this achieved? We will do something, that is, we will ensure that the highlight and the midtone areas maintain a very good contrast and they are almost similar to a 45-degree straight line passing through the minimum density point in the independent axis, and following that midtone region we will start to reduce the contrast in the shadow areas. That means we will basically be starting to compress the uh, tones in your shadow areas. So what is the advantage of doing this? First of all, we will get a better contrast in both the highlight and the midtones, and we know that if we get higher contrast, meaning what, we will get better number of tones in the reproduction with respect to the original. So we know even a small increase in contrast in the highlight area is perceptible by the human eye. So we are more concerned about the highlight midtone area than we are in the for that shadow area. So we have that ability to compress the data, to compress the number of tones in the shadow area, whereas increasing the contrast or keeping the contrast of the highlight and midtone areas uh, very high, nearly ideal like situation. Okay, so we saw this particular graphing tool uh, which will help us to better identify that and better plot the data, so that this is a graph where the intervals in the highlight areas are much more uh, widely spaced, so that even a small change in variation or in the tone in the highlight area is more drastically understandable when you plot it in this particular curve in this particular graph than in your normal linear type of a scale, graphing scale. And your intervals in the shadow areas are less widely spaced. That means they are very closely spaced. So even if there is a greater amount of change in the contrast of the tones in the shadow area, that will not be easily or drastically visible in this particular graph. Okay. Now the question is, I have established that the perfect nature of my tone reproduction curve for my print mechanism is this one. Let us say this is my uh, ideal situation. I want that all my reproduction follow, or at least some of my reproductions follow, this type of a tone reproduction curve. Okay, but you see, it's easier said than done, because you will understand why this is more complicated than today's work. Because I'll just give you one example, I'll just show you one example, a very small demo, then you will be able to understand. Okay, so try to think about it. You have with you the final tone reproduction curve that you want for your print, right? But you are not printing directly in the sense you are not printing directly from the original. You have some intermediary steps. What are these intermediary steps? You have to prepare the negatives. You have to, if you are doing indirect process, then you have to prepare the positives also. And finally, you get onto the plate, which will be ultimately used for the actual print operation on the media. So you are basically kind of dependent not only on your ultimate reproduction, but you are also dependent on kind of, you can say, the nature of the reproduction that you get in your negatives as well as in your plate. In order to control, you have to understand this, realize this, only then we can move on to the next topic that I wanted to discuss in this lecture. In order to have or get this type of a tone reproduction curve for your ultimate printed reproduction, you need to have a precise control over your negatives and your transparencies and your plates. That means you need to identify for what transfer curves or tone reproduction curves of the image that you are getting in the transparency and the plate, you will get a tone reproduction curve for your printed reproduction, right? Because you are dependent, your ultimate printed reproduction is dependent on the nature of the negative and the plate. So in order to affect or impact your tone reproduction curve for the ultimate printed reproduction, then you have to also identify and kind of determine for what nature of the tone reproduction curve in the negative and the plate do you get a tone reproduction curve of this nature in your printed output, right? So this is basically, we will approach this problem from the backward end. Okay, so we know our output, right? So from that output we will determine the necessary tone reproduction curves in the film as well as in the plate, which will give us this particular tone reproduction curve for our printed output. This is basically done with the help of a tool which is known as the Jones diagram. Okay, this is basically known as the Jones diagram. It's a very powerful and a very useful tool for identifying the for what values or what nature of the tone reproduction curve we will be in the negatives as well as in the plate. Do we get our required tone reproduction curve in the printed sheet, right? So you can see over here that there are four quadrants, right? So let me mark the quadrants: quadrant 1, 2, 3, and quadrant 4. So I will talk about the individual quadrants. From all these quadrants, I think at least two quadrants are familiar to you. What are these quadrants? Quadrant 1 and 4. What does quadrant 1 and 4 represent? They represent the quadrant 1 represent the tone reproduction which you want, which you have decided that okay, you have taken a graph paper and you have measured the data from your printed output, and you have reached at this particular point. Okay, and then you have thought, okay, maybe I will not compress my data this much, maybe I'll compress the tone reproduction curve till this much. So whatever your suitable uh, measure, whatever your suitable understanding of the printing process is, whatever your requirement during that print production process is, you will determine, you will just draw a tone reproduction curve likewise. So that is what has been represented in quadrant 1. So the desired 4-color reproduction curve is this one. Okay, this is your 4-color reproduction, this one, right? And you have also obtained a similar type of 3-color reproduction. So I'm not talking really about the black channel over here, the black reproduction curve over here. I'll talk about it in the end. So we need a different sort of analysis over there. So I'll be talking mainly about your 4-color reproduction and your 3-color reproduction. All right. Now, this is what you want. Ultimately, after doing all the necessary corrections, after finding out for what values of negative transfer curves and plate transfer curves, you want to get this type of a tone production curve for your 4-color reproduction. What you have to do, you have to go from the last stage to the first stage, because what data do you have with you? You have this particular data, this particular curve you have. Now you are trying to estimate for what tone reproduction curves in the uh, negatives and the plate are you supposed to get this type of a tone reproduction curve when you print, ultimately print using those negatives and those plates. Is it understood to you? So we will analyze this all the 4 quadrants, and then we will be trying to understand what each of the quadrant basically means. Okay. So as I was saying, in quadrant 1 you have your required or optimum tone reproduction curve, right? Now let us see what you have in quadrant 2. In quadrant 2, you have to plot the percent dot area of the halftone negative for each of the process color versus the density of the 3-color reproduction that you have measured using your um, densitometer. So let us try and understand what this all means. So I said a lot of things. Let us try and understand. Hopefully, quadrant 1 is okay. Quadrant 1 is understood by you. Now let us try to understand or decipher what quadrant 2 data means. So for that, let me just draw something. So for example, you have taken out prints from uh, each of the inks. That means you have a print for CMY as well as CMY, right? So this is the data, 3-color data that you have plotted over here, and as well as you have a data that is CMYK, which is your optimal, that you have plotted over here, right? Now in quadrant 2, this is known as your plate press end. That means this is ultimately your press data. What you have to do is you have to plot two things. Now in case of quadrant 1, you see both the axis over here is plotting density data. This is also density, this is also density. This is the density of the original, this is the density of the reproduction. But in case of quadrant 2, the density in the negative x-axis, this is basically changing. This is what this data is, basically the percentage dot data. So now the question is, where will you get this percentage dot data? See, in your previous lecture, I already showed you that grayscale, and I told you that while printing each of the plate, each of the sheet, for cyan ink, there is a grayscale stepwise, right? This will contain all dot percentages, like maybe this is 10%, 20%, up to 100% dot. Similarly, for magenta also, another stepwise will be printed along with the magenta sheet, right? That will also contain 10% to 100% data, right? So like this, you will have dot percentages for each of the printed sheet of paper, right? You have to measure the density of each of the dot percentages, right? So in the y-axis over here, what is there? You in the along the y-axis, there you have the density of the 3-color reproduction, right? So in this x-axis, you have the dot percentage. So what you have to do, you have to plot the dot percentages, printing dot percentages versus the density of the three color reproduction for each of the printer. That means for cyan, magenta and yellow. Black I will talk, as I told, black I will talk later on. Is it understood now? So for example, let me, so like this I will not be able to explain very well. Let me draw myself the entire thing, then you will be able. So let me try and draw the entire thing, okay? So this is basically your plotting area. Now what is your four color reproduction? It is something like this, and your three color reproduction is something like this, right? Okay. Now what you have to do is, in this axis you have the density of the reproduction, in this axis you have the density of the original, in this negative x-axis you have the percentage dot, right? So this is basically 10% dot, 20% dot, up to your 100% dot. Okay, now see what we have to do. What we have to do is, basically, in order to understand this, we have to plot the grayscale percentage dot that we have obtained from each of the printer versus the three color density. So how this can be done, let us try to understand how this we will be able to achieve this. So for example, so let us this be the various densities. So what you will do, so let us say, for example, you have a density of maybe zero point 0.1, right? So for zero point 0.1, for which so first of all we are talking about the cyan plate. Okay, so we are preparing the plate end curve for the cyan plate. That means we are plotting the data obtained from the cyan colored print, just the cyan colored print, the dot percentage data versus the density obtained in the three color print. So this is your three color print CMY data, this is your four color print, that is CMYK data. So for a 0.1 density, naturally you can it is well understood that the this particular data will be generated by a dot percentage which will be having lower dot percentage, right? So for example, if I am talking about this 0.1% data, so naturally 0.1 the density will be obtained from a point, maybe for a dot percentage of 10. So like this, you get a point like this. Okay, this is the first point. Similarly, for a density of zero point 0.2, then you get another plot like this. Okay, similarly, for another, maybe this is 0.4. In this situation, you will get a point like this, and maybe that will be obtained by a dot percentage of, let us say, 40%, let us assume. Okay, so we'll get another point like this. Like this, you go on joining the points like this for each of the, this is a plot that you got for the cyan plate. Similarly, you can get a point, another plot for the magenta plate and the yellow plate, like that. Okay, so this is how you get the data in the second quadrant. The second quadrant plots the data of what printing dot percentage is required to produce a certain density. Let me put it this way. I am saying the data in the second quadrant is plotting that for what dot percentage I will, for each of the plate, that means for the cyan plate first, for what dot percentage will I get this particular density, for what dot percentage will I get it, cyan density of this much, for what dot percentage will I get a magenta density of this much, right? So this data, that is the dot percentage of each of the plate versus that of the three color three color print density, that is being plotted in the second quadrant. So coming back to our original discussion that we were having, now the data about that we are talking, the data about your uh, third quadrant that we want to prepare, right? So what is there in the third quadrant? So let me just remove this, then I will continue my discussion. The third quadrant data is used to generate the characteristics of the ideal half-tone separation negative that will be needed to make in order to get the desired reproduction plotted in quadrant 1. Okay, so here you will see in quadrant 1 this relates to the density of the original to the percentage dot area of the negative. Hopefully you are able to see that along the x-axis, negative x-axis in the third quadrant we have the dot percentage, whereas along the negative y-axis we have the density again, right? Here what you have to consider basically is this one. This data that we have obtained in the third quadrant is telling you that what dot percentage is required in order uh, to create what density. Now you may say that okay, but we have already seen this, haven't we? Where have we seen this? This we have already seen in quadrant 2. Here each of the point that we get in this particular one, we are saying that for, because this is, I've already told you that this is basically your plate press curve. Now this quadrant is telling you for what percentage dot is required to be printed to achieve what density. So for example, if you want to know that in your plate, uh, in order to reproduce a density of, let us say, 0.4 in the cyan plate, what dot percentage in the plate is required. So what to do? That is how you have done. You have just continued this, plotted this point from the three color density, and you have continued this and brought it down. So brought it down like here in this particular point here, and then you have moved down to find out for what dot percentage a certain density, or what percentage is required for reproducing a certain density. That is what you have done basically, right? This is for your plate data. This is representing your plate data. That means it is saying that in your plate, in your cyan plate, in your magenta plate, in your yellow plate, what percentage of dot is required for reproducing what density. Okay, so how you have done? You have just taken the all the data from your three color reproduction and you have plotted along this particular dot percentage in order to, and you have plotted these curves in order to obtain the plate end curve, right? Similarly, in case of quadrant 3 also, you are trying to find out for what percentage dot is required for reproducing a certain density. So how, now the question is how to reproduce this particular data in the third quadrant. To find out the data in the, to calculate the data in the third quadrant, we have to choose a point on the original x-axis in the first quadrant. Then we have to trace up to the desired three color curve, then across to the curve representing the particular printer that is plotted in the second quadrant. Again come down to the third quadrant, draw a line, and again from the starting point in the first quadrant we have to then go down to the transfer curve that you can see in the fourth quadrant, and we have to then shift left, and the point where these two lines meet, there you will join, you will find out a point of intersection, and ultimately when you have multiple such points you will join those points to obtain the curve. Now this is not understood, but I know this you could not understand this obviously because this is a curve and I need to draw it myself. So allow me to draw and explain it to you. So I will try to draw what I have just explained to you. All right. So what I am saying that how to obtain the data in the third quadrant. What is the data in the third quadrant? You want to know for what dot percentage you can get a certain density. See, think about it for a minute. Okay. What did I say? I said that in the first quadrant you have already found out what is your optimum uh, tone reproduction curve. This is optimum tone reproduction curve for your three color. This is the optimum tone reproduction curve for your four color. Since we have not talked about black printer right now, so I'll be talking about it at a later stage. Focus on this data. Now the question is, how do I create my transparency as well as my plate to ensure that the tone reproduction curve ultimately when I print that paper or that image follows this particular line. That is what our problem statement is. We have already done that for the plate. How we have done that? We have simply taken a certain point in the your three color reproduction like this. For example, this is your density in the original. We have moved up to find out what density is obtained in the three color curve. Then we have moved leftward, and then we have calculated or we have plotted the data that we are getting in the uh, individual printers. That what is that data? That is the dot percentage for each of the plate versus the density for the three color print. That that data I have plotted over here. Now after plotting that particular data, I have obtained this type of curves, right? Now these curves represent the tone response curves for tone reproduction curves in the plate for each of the printer, that is for cyan, magenta, yellow, etc. Right? Now we are talking about how to do the same process using your in your for your films. Now I want to find out that for what dot percentage I need to reproduce in my film in order to get densities after certain densities after printing. I want to reach here, right? I want to reach at this particular point. I want to reach at this particular point, but I do not know what type of what type of dot percentages I need to reproduce either in my film or in my plate. All right. I have obtained the data, or I have obtained what type of dot percentage I need to reproduce in my plate, but I have not done is the type of dot percentage I need to reproduce in my film to achieve this particular tone reproduction curve after printing. So let us see how it is done. For example, let this point be 0.2 density, let this point be 0.4 density, whatever. Okay. So for I need to find out the dot percentage required in the film or in the negative that will lead to the formation of an area of that particular dot percentage after printing, whose density will be zero point 0.2 or 0.4. I'm repeating once again. Okay, I want to find out, my goal is to do what? I want to find out what dot percentage I need to reproduce in my negative, so that ultimately after printing I get a printed image which follows this particular tone reproduction curve. That means these densities are to be followed, right? So let us see what is done. So in order to find out you can say the what dot percentage is required in your negative in order to reproduce a density area of zero point 0.2 after printing. Okay, so our intention is that to reproduce, to find out the dot percentage from zero point 0.2 density. What dot percentage is required for 0.2 density, right? So what you do, you just start to move up. Okay, you start to move up, right? Then you move leftward, right? Okay, as soon as you move leftward for the certain maybe this is your cyan plate, right? You hit this particular plot, right? Then as soon as you hit this particular plot, then you go down, right? And you continue this line. Similarly, for let us say for another point, that is for another you want to find out what dot percentage in your film is required to reproduce a density of zero point 0.4 after printing. So how to do that? 0.4, you go up, then move left. There you will hit the cyan plate curve over here. Then similarly you go down and continue drawing the line over here. Okay, now in the fourth quadrant we already have got the transfer curve. What is the transfer curve? Transfer curve is the ideal curve. So in this situation you have the density of the reproduction over here, and this is the density of the original over here. So see, in your first quadrant and in your fourth quadrant, in both the quadrants over here you have plotted data of density versus density, right? So in this situation you have, this is where you have left off. Now how to find out the points because you have just drawn some lines. Until and unless another line intersects this, you will not be able to find out the point of that particular curve in for that preparation of that negative of that particular sign separation, right? So how to do that? Like you wanted to find out what dot percentage is required, and you moved up to draw this type of line. Similarly, in order to find out the intersecting point, you need to come down, right? You need to come down, right? And you see, as soon as you come down, this line hits your transfer curve, and the point where it hits the transfer line, you draw another line in the left direction. Okay, fine. Next, similarly, for another density, that is 0.4, you need to find out another intersecting point in your third quadrant. You come down, and the point where this line hits the transfer curve, from that point onward, you start moving towards the left. See, this is the line. This particular line is for which density? For 0.2 density, right? So you got this particular, let me change the color, otherwise it's becoming more confusing. This is the point for what density? For 0.2 density, right? And these two lines, this line and this particular line, is for which density? For 0.4 density, right? So you got this point, you got another point for the sine curve. Similarly, if you get, you will if you plot all other points, some more points, maybe 5-6 more points, right? You will be able to get points like this. Then what you have to do, you have to simply join these lines, and you get, although I'm saying cyan, I should have used cyaning, but I used red ink, doesn't matter, but I get a tone reproduction curve for what? For the cyan, ideal cyan separation negative. When I am preparing my separation negatives, if you remember our class in that photographic masking chapter, in that lecture, what I told you, you have to use a mask whose transfer function or whose characteristic curve is such that after adding both the transparency plus the mask, the resultant you get of a certain nature. So you know what, this is a back calculation, you know what the tone reproduction curve of your cyan separation negative, that means the resultant negative will be. So you have to use a mask which will add up with the the original to reproduce a cyan separation negative having such a tone reproduction curve. Similarly, you can do for a magenta ink, etc. Magenta ink also you can do for yellow ink also. Such curves you will be able to get, right? Hopefully this is clear, this part is clear. So let me just from the beginning again, and let me just repeat this entire thing in a nutshell, so that everything becomes clear once again. Okay, so what did I say? Our intention was to find out, for what our main intention was to find out what is the dot percentage required in your plate as well as in your film, which will lead to creation of certain densities after printing. That is the ultimate goal over here, and be very clear about it. Okay, so we have divided into 4 quadrants: 1, 2, 3 and 4, right? So this is your expected, or this is what you are expecting maybe. Okay, this is for your 4 color, this is for your 3 color, right? This is you have created this type of plots. Okay, this is your density of the reproduction, density of the original, this is also density of the reproduction, this is the dot percentage, this is the dot percentage. Okay, first let us prepare the plate curve. Okay, how to prepare the plate curve? You have to plot. So this is basically, we'll have data like 0.2, 0.4, here also 0.2, 0.4, here also 0.2, 0.4, etc. And in this axis actually you will have dot percentage of 10% up to 100% dot. Okay, right? This much is clear. Okay, now let us find out for what or how much percentage dot is required to reproduce what density of what density. Okay, so how to do that? In your second quadrant, you have to simply plot the dot percentage that you have obtained after printing. So for example, in your cyan printer, you have printed something using only cyan using only cyan ink, there you have used a particular step wedge. So you know, for let us say, you know, for each step wedge, like this is 10%, this is known to you, this is 20%, 30%, and up to 100% you have, right? So what you have to do in the second quadrant, you just simply have to plot the dot percentage versus the density of the three colors for that particular printer. So for example, if you print, if you have obtained the you plot these two data, and you will find out, so this will be your cyan, this will be your magenta. Similar, they follow magenta and yellow, follow the similar pattern, they will have the same type of graphical nature, I mean the curve nature, right? So in this case, in your second plot, you do not have to do anything. You just have to calculate. You have to measure basically. What you have to measure? You have to measure that for the cyan, when we are preparing the plate curve for cyan, what you have to do? You have to measure what is the density in the three color print for which you have a 10% dot, right? In your cyan printer, what is the dot percentage in your cyan printer for a certain density in your three color print, right? What is the density in your what is the density of your three color printer for 30% dot in your sand printer? So this is how you have to just measure the data of your three colors print, as well as your dot percentage that you have obtained after print through printing the step wedges, and you have to just plot that data, right? This much is clear. Now the question is, and of course your fourth quadrant is basically the transfer curve, which is your ideal nature of the curve of what will be the nature of the curve in ideal situation, the 45-degree line passing through the origin, right? Now the question is, in third quadrant, what you have to do? You have to find out the dot percentage in your negative for which you are getting a certain density after printing. Okay, so for, let us say, for we want a density of, let us say, 0.5. Okay, we want to find out, basically we want to find out the how much dot percentage in your negative is required to reproduce a density of 0.5 after printing. That we want to find out. Okay, so for, let us say, first is the cyan separation negative we want to prepare. Okay, so what you have to do? You just have to go upwards. You have to find out where it meets the 3.3 color combination, move leftward, find out where it intersects the cyan cyan curve. Then you have to come down and continue drawing the line. In order to find out the intersecting point, what you have to do, let me just now I will do it correctly. Okay, so I'll use the correct color for the cyan ink. Okay, now similarly, as you went up, you have to come down and you have to find out at which point this it hits the transfer curve, and then from that point onward you have to move leftward and find out the point of intersection between these two lines, and this will be your density, this will be your dot percentage. So let us say this is your 40%. So in order to reproduce a density of 0.5 after printing, the cyan separation negative in that area should print or should create a 40% dot. Similarly, other points also you might get like this. You simply join these points together. For other printers also, you can join these points together to find out in your negative how much dot percentage is required to print what density after the print operation is over. So ultimately, see what you are doing. You are starting from the printed output, right? From the printed output, you are going backwards. That means you are trying to find out, okay, I have this density. I do not have, but I want this density. I want a density in my three color reproduction. So let us say it is 0.5. This point only. In order to reproduce a density of 0.5 after printing, in that area, what should be the dot percentage that cyan separation plate should print, magenta separation plate should print, and yellow separation plate should print, right? So similarly, from that data you can that data you will obtain from the plate curve in the second quadrant. And if you follow what I have just told you, the process, then you will be able to find out what in your, from the third quadrant data, you will be able to find out, okay, if I want to print 0.5 percentage data in a particular area in my after printing in my 3-color print. What is the percentage of dot required to be printed by the cyan separation negative, for the magenta separation negative, for the yellow separation negative? So ultimately you are trying to equate, not equate, I will say it, you are trying to correlate for what dot percentages of the separations certain densities will be created. That is our goal, or that was our intention when we started doing this exercise in the first place. I hope you will agree. We wanted to find out what should be the nature of the negative, what should be the nature of the plate, in order to obtain a print of a certain characteristics. We know this is the print of the certain characteristic, this is what we want. Now in order to obtain this, what is the nature of the plate I have to reproduce, what is the nature of the negative I want to reproduce, right? So this is basically the method using which the Jones diagram method, using which we can find out that for what dot percentages I need in my film, ultimately in my plate, in order to reproduce a print having a certain characteristic or tone reproduction curve. So hopefully this part is clear. Now let us start to talk or discuss a little bit about the black, how to do the same process for the black. Now let us talk a little bit about how the black printer data is being generated. So for understanding the importance of black printer, we have to go back a little bit earlier to remember the concept of additivity failure. Sorry, let me just change the ink. Yeah, the concept of additivity failure. What does it state? The additivity failure states, the problem of additivity failure states that the density of the combination is never equal, is always less than the sum of the individual densities obtained through the particular filter, right? So what you have to do? You have to find out, in case of identifying the black printer, what you have to do one calculation. What is that calculation? If you take a look at this particular data over here, you see there is a distinct difference between the 4-color and the 3-color densities, right? Why is this? We all know that they are deficient in hue, and when this black printed data is added, densities are added to the 3-color data, only then we will reach the 4-color densities, right? This is known to us. Now what we have to do, we have to compare the actual density printed by the black printer for any particular point in the original scale to the amount of change in density caused by the black printer between the 3 and 4-color reproduction. Now if we plot this particular data, then what we will get? So for example, let me just draw this data. So what did I say? I said you have to compare the change or difference in density. So for example, let us say that this is the density of the 4-color reproduction, this is the density of the 3-color reproduction, right? Now what you have to do, you have to find out the difference in densities when we are using the black printer in black printer for any particular point on the original scale, and the amount of change in the density that is caused by the black printer between the 3 and the 4 colors. So if you take a look at the your plot over here, you can distinctly identify, if you just calculate this only, right? So if you just calculate this data only for the same density in the original, what is the difference in density between the 3-color and 4-color, right? So how to calculate that? So for example, this is, let us say this is 1.2, this point is 1.5, similarly this point is 1.5, this point is 1.6 maybe. So like this, what you have to do, you have to simply point out the differences. Oh, I didn't, this was not in the foreground, so let me draw it once again. You know that your 4-color print looks like this, and your 3-color print looks like this, tone reproduction curve. Obviously there is a distinct difference in the densities, right? So for the same density in your original, the density of the 4-color and 4-color is this much, and density of the 3-color is this much, right? That means the density of the 3-color is less than the density of 4-color. That is natural, that is going to happen, right? So you have to plot the data that the black printer brings on when it is added to the three color uh, prints. That means you have to find out the difference in densities between the three color and the four color prints. Okay, so if you plot this density somehow like this, so in the x-axis obviously you have the density of the original, and in the y-axis you have the difference in density, right? You have the difference in density. Okay, so this is 0.2, this is 0.4, this is 0.8, this is 1, let us assume that. Okay, and similarly this is also 0.1, 0.2, maybe something. Okay, this is a plot where we are plotting what data, what versus what. We are plotting the difference in densities between the four color and the three color prints versus the density of the original. That means essentially you see this difference is there, difference of density between the four color and the three color prints. We are basically trying to identify this difference only. So you see, as we move from the highlight towards the midtone towards the shadow area, the density is increasing or decreasing. Sorry, the density difference between the four color and three color prints are increasing or decreasing. It's increasing, obviously. So what do you think will be the nature of the plot over here? It will be something like this only, right? Because it is increasing. The difference in density between the four color and three color prints due to the addition of black is increasing, right? This much part is clear. Now if now the question is how to plot this data. Now you see, the black printer will be used to make up the difference between the three color reproduction and the four color reproduction that we have seen. From the data now that let me just yeah, reduce this. Okay, so here as you can see from this particular data over here, you can very well understand uh, that the black is needed only in the shadow areas, right? What you have to do is we have to first analyze the differences between the three color desired reproduction and the four color desired reproduction in quadrant 1. Okay, now for any given point on the original scale, the difference can be determined by subtracting the three color density from the four color density. That is how we have, reproduced kind of this particular plot over here. The differences between the four color and the your three color prints. That is how we have generated the data of the difference in density versus the density of the original, right? Now from this, what you have to do, determine the halftone characteristics of the ideal black halftone negative by tracing in both directions from the original axis in quadrant 1 and on the Jones diagram until sufficient points have been plotted to generate the black halftone negative. So ultimately what you have to do is basically similar to the data that was obtained, the percentage dot data for each of the subtractive colors that was obtained using a certain method. We have to obtain the black data, black printer data for the negative as well as for the plate using the same principle. Like, so how did we obtain the plate data for other colors? We just did what? We printed a test patch having different dot percentages and found out or calculated the densities. We plotted the dot percentages of those individual plates versus the three colors. So similarly for finding out the your black density, black percentage also in the plate, we have to use a certain, we have to print the black test target. That means we have to print a sheet of paper where we will be printing this area where there will be 10 black dot percentage, 20 black dot percentage, ultimately 100 dot percentage, and we have to plot this dot percentage data versus the black density data that is wanted over here, right? How did we get this data? How did we get this particular curve? We got this particular curve, if you can take a look at this, we got this particular curve by calculating or plotting the difference in density versus the density of the original. So we will get this type of a this type of a curve like this, right? So the nature of the curve that I have drawn should have been like this actually. So let me just redo it. I later realized that I made a small mistake in the nature of while drawing the nature of the curve. Okay, let me just redraw it. Okay, so the nature of the curve will be something like this. All right. Now coming back to our original discussion. So we have the black data. So how did we obtain the black data? By plotting the difference of densities that we got from between the four color prints and the three color prints versus the density of the original. By plotting these two data, we obtained the black desired black tone reproduction curve. So after that, we have also printed a black a sheet of paper with only the black areas along with a step fetch like this, where we have the different dot percentages, 10% or 20% or up to 100% dot, right? Now what we have to do, similar to the previous examples, as I told you, in order to create the plate data, you have to plot the dot percentage for the black printer versus the densities of the black printer, that is a wanted black printer, right? So we get a plot like this. Similar to this, what we have to do, we have to see, remember this very carefully, we are not printing black in the highlight and the shadow areas, we are printing black mainly in the, sorry, we are not printing black in the highlight and the mid-tone areas, we are printing black mainly in the shadow areas. So that is why we are getting densities upwards of 1.3, 1.5, and here also that corresponds to shadow area. That means here also we are getting that same density from a dot percentage of 60 to 100%, right? So plate data for the black printer, that is obtained and that we have found out. Now similar process we have to do for generating how much dot percentage is required for the black separation negative to reproduce the said density of the black printer, right? So what to do, you again do the same principle. So for this particular percentage of density, come and where the data hits, I mean where the plot hits this particular line, you draw a vertical line. Similarly, you draw another vertical line through this axis, and where it hits this particular transfer plot, then you draw the line. Similarly, you will notice that you have got certain points, certain like your cyan, magenta, yellow points that you join to create those uh, tone reproduction curves for your negative. Similarly, you will get your tone reproduction curve for your black printer. Okay, so this is basically how you draw the tone reproduction curve for the black printer as well. Okay, now hopefully this is, and whatever I told you was understandable to you, because you see this has an advantage. What advantage, you might ask? That it removes any sort of trial and error process. Okay, for example, you do not know what dot percentage. If you did not have this technique, you would have just randomly thought of certain dot percentages and actually found out that okay, maybe in order to reproduce this density, I need this dot percentage in my plate, this dot percentage in my film. That may or may not have been correct. But here you only need a graph paper. With a graph paper and a few printed sheets and a densitometer, you can very much accurately reproduce some negatives as well as plates, which is guaranteed to have dot percentages that is going to reproduce those densities that you were expecting them to reproduce. So this basically eliminates all sorts of trial and error, multiple iterative processes. These are all eliminated, and simply you need to identify your what should I say, optimum tone response curves for your four color prints, three color print, and your black printer. And then from this data you can prepare a tone response curve, tone production curve for your plate, as well as from that you can ultimately prepare a tone production curve for your film negatives. And once it is done, the entire process becomes simpler. So you know now that from the very beginning, in order to reproduce a certain type of a print up to your expectation or as per your expectation, what kind of dot percentage I need to produce in my negative to create certain densities, what kind of dot percentage I need to create in my plate of cyan, magenta, yellow, etc. separations in order to reproduce the print having a certain optimum or tone reproduction curve of my choice, right? So this is a very powerful tool. Jones diagram is a very powerful tool which is basically giving you a method to correlate between the expected densities and what are the necessary dot percentages required to create those expected densities. Okay, so as I told you that uh, this particular work becomes very much uh, maybe it looks easy, certainly easy, and it has certain advantages because trial and errors and everything is removed. But albeit even in the digital space, we will use not exactly this, but techniques similar to this when we go to the digital domain. Okay, so this is what I wanted to talk about tone reproduction. So with this we come to the end of the tone reproduction part, color tone reproduction part, and how to analyze it, analyze the characteristics of the tone of the printed output from the tone reproduction curves, and of course how to modify the behavior and how to change the nature of the negatives and the plates in order to create prints of a certain tone reproduction curve. Okay, so in the next, from the next lecture onwards, we will be talking about something very important, which is known as gray balance, and how to achieve gray balance using equivalent neutral densities. Okay, so thank you for listening to this lecture.